Welcome everybody for this second day of this very nice workshop. So it's my pleasure to introduce the first speaker of this afternoon, Yunan Yang, who is going to talk about optimal transport for learning chaotic dynamics via invariant measures. So thank you.
Yeah, thank you very much for the introduction, and thank you very much for the invitation for me being here. It has been more than 2 months. I think it just goes so fast, I cannot believe it's already 2 months here. So today I get this chance to present something I worked on very recently with my collaborators, Lagrangian, Elisa Negrini, Robert Martin, and Maisha Pasha. So I have a short story to tell. So I never know of any of them in person. So we started the collaboration through Zoom, and so far till today, I only know there are 2D projections. So, but it kind of worked eventually. So we started it from this IPAM workshop last year, about April. That's when pandemic just happened. And then thanks to Adam Oberman, who brought us together and say, if you want to work on something, but he disappeared in the middle. So we continue to work on something. And 1 year later, we have this work. And it's also, it's very interesting experience. So, so today I'm mainly talk about one of the papers, and you can find the preprint online. It's on arXiv. So before I continue to the details, I want to introduce the notion of Lagrangian and Eulerian. Maybe not be the most accurate way of using the two adjectives, but whenever I say Lagrangian perspective, I mean I'm in the particle perspective. This is the picture from this very famous book, Transport Phenomenon. So if we are tracing with the particles, then I'm going with the particle, like the particle changes with the time and it's a trajectory. And I use this particle trajectory to describe what is the fluid, what the properties, physical phenomena, etc. And if I'm using the word Eulerian, which means I'm actually in the probability distribution perspective, I'm in the road part. Well, you as an observer, we are fixed at XYZ location, and we just look at how many, what's the property of the fluid, what's the density that's flowing around, and what's the momentum. So we are fixed. So that's what I mean being a Eulerian perspective. I find that a lot of the things we deal with, especially in computational fluid dynamics and also solid mechanics, you have this opportunity to interchange between these two. Most of the time, about one physical phenomenon, you can either use a particle perspective to describe it, or you can use a Eulerian perspective to describe it. And that gives us a lot of flexibility, especially in dealing with inverse problems. And another similar situation occurs actually in the waves. You can characterize waves by a wave equation, but you can also characterize waves by the Helmholtz equation in the frequency domain. So those interchanges was also very beneficial in that aspect. So today I'm going to change from Lagrangian to Eulerian and to gain some stability and the well-posedness of solving the inverse problem. Okay. So first of all, I want to emphasize that we are dealing with chaotic dynamical systems. And whenever you use the word chaotic, you are already in a deterministic setting. And the reason it is chaotic is what is happening locally doesn't really tell you what's happening a long time, a very long time later. So here what you see is a very famous Lorentz 63 model with only 3 parameters, but these 3 parameters, sigma, rho, and beta, have their own physical meanings. And a very simple setup for the inverse problem is I observe time trajectories from this ODE system in terms of time t0 all the way to tn. And the question is, will you be able to tell what is sigma, rho, and the beta? So such questions are very relevant, especially when our collaborator was at Air Force Laboratory. So for example, if you want to create a digital twin of some realistic aerospace modeling, you always have to do model collaboration to find the best parameters. So that's, there is a Appalachian background why people are interested in such phenomena. And most of the time you observe trajectory data. Okay. So, well, the previous one is the Lorentz 63 model proposed in 1963. So that there you have 3 parameters, but nowadays you can have more like advanced way to parameterize your model, because what you don't know is entirely the right-hand side, is entirely the Lagrangian velocity. So if you know a lot of the physics, right, like Lorentz, you know a lot of physics, you can parameterize it by sigma, rho, beta. But if you don't know it, it's also fine. So there's some literature, like for example, if you parameterize your entire right-hand side by polynomials, global polynomials, then you can find the basis coefficient, and that's give rise to the work Cindy in PNAS from the UW group up there. And also there's another group that I know, Schaefer, Chuan, and Ward. So if you can parameterize the right-hand side as a linear combination of your polynomials and try to find the basis coefficients, and that become a sparse linear algebra problem. Or you can use other basis function, which I just learned from Sui Tang in the previous seminar talk. It can be piecewise polynomial. That's also give you a lot more freedom. And again, you can learn the coefficient and other basis function for all kind of Chebyshev polynomial, Lagrange polynomials is also free to choose. And also very recently, there's a lot of literature in parameterizing your entire right-hand side by velocity field by neural networks, based on probably a very good approximation theory from neural networks. That's even more references. So no matter how you parameterize it, physically or polynomial or basis or some other way to parameterize it, in the end, you have to find the coefficients. You need to find the weights in the neural network case or the coefficient in the polynomial case. And I will denote this entire coefficient to be theta. So if we are sticking with this Lagrangian perspective of the problem, then what is our data? Our data will be just the time trajectories observed in the time domain. Okay, and the inverse problem will be, let me just work with these time trajectories and try to find what is the coefficient, no matter it's physical or they are just polynomial basis or they are neural network weights. So that's the framework, and that's actually a lot of the works have been based upon, this is the mainstream way of doing that. So this is a very nice way to do and a very standard way to do inverse problem in this case, except there's an actual level of difficulty come from chaotic systems, which is the famous butterfly effect. So I have two trajectories. One starts with 10, 10, 10, it's a spatial location, and another one starting with 10.001, 10, 10 as a spatial location, and I run it. So at the beginning, since it is such an epsilon change, I don't see any difference in the first 10,000 time steps. But afterwards, you can see these two trajectories deviate from each other ginormously. And that means where I no longer, that is actually the chaotic behavior that a locally propagation give you a really, really bad deviation in a long time process. And unfortunately, when you observe the data, you see this huge difference, but this huge difference has nothing to do with a wrong parameter or not. This huge difference just comes from the chaotic behavior of the dynamical system you are working with. And in inverse problem language, for us, that's eupostness. Okay. And also on top of that, this is just chaotic by definition, chaotic system. But on top of that, if you have intrinsic noise, which means when you were modeling the dynamical system right-hand side, there's a little bit noise in it. Or there's extrinsic noise, which means you already measured the dynamical system, the trajectory, but just when you do the measurement, there's a little bit perturbation when you're recording it. Then you also get entirely different trajectories. So on the right-hand side in this picture, I show these three situations: no noise versus intrinsic noise versus extrinsic noise. And such noise, as you can imagine, they accumulate again thanks to this is a chaotic system. So such difficulties make it very intractable in the sense that you can really, you may not be able to trust your reconstructed parameter because it could really just come from this, could just come from epsilon in the initial condition. And in realistic situation, you never get a solid hold of the initial condition. So such difficulties motivate us to have an alternative way of solving that. And the idea is to look at what they share in common and to explore the stable information among those unstable or chaotic time trajectories. So in this paper, we considered three attractors, Lawrence, Chen, and Ressler, and they all can be characterized as chaotic systems. So next is the idea. So although they are chaotic in terms of very sensitive to the initial condition or very sensitive to the noise, but there are some well-defined statistical properties. So first of all, if you give me a long-time trajectory, I can define a so-called occupation measure. So what is the occupation measure? In terms of numerical aspect, it is binning, it is a histogram. If you give me a long-time trajectory, then I just divide this domain into boxes and count how many times this trajectory goes through that box. And if it goes through once, then I count it as 1, and then divided by t, which is equivalent to divided by the total number of steps. So if you give me a time trajectory, I will be able to obtain an occupation measure, and it of course depends on how you discretize and how you define the histogram bin, right? But this one is easy to obtain. So once we have this occupation measure, and the nice thing is this is highly related to the Sinai-Rule-Bowen measure called RCIB measure in the context of a dynamical system, which means if you run the time trajectory long enough as t going to infinity, then your occupation measure will converge to the physical measure mu star. And then this is what we can refer to as a physical measure or invariant measure or SRB measure. And then this invariant measure by its definition is no longer sensitive to the initial condition, but just by its definition, it's invariant measure. And also that's something we can obtain also from the trajectories. So the idea is instead of working with the long-time trajectory and working, just trace the time and the particles, we just work with the measure, which is easily can be transformed from my long-term trajectory. Okay, now we have a data that is much more robust to noise, as you can see in this case. So the first row is the time is the accumulation binning process, occupation measure with no noise, while the second row is with intrinsic noise, and the last row is with extrinsic noise. Although they have slightly difference, but if you observe the geometric features, they have very similar property. And if I use an objective function that's kind of robust to such minor differences, I will get a pretty good inverse problem reconstruction. So that's to.
Could you just say again? So is your physical measure, is it literally the SRB measure, or is it something slightly different?
I think as physical measure is RCIB measure. It depends. I think at least the reference we refer to, they call them the same thing. Yeah. Well, what we can always numerically get, I think it's going to be an approximation to that RCIB measure. So that's why I refer to this as occupation measure, because this is what I obtained by binning my trajectory. So now we have a more reliable, a more stable data transformed from the trajectory. Next is how can I get a model? Because inverse problem, you know, the way we solve it is you have a guess for the parameter. You see the data and you compare with the with the reference, and you see, they are not the same. Let me change the parameter again. So we have to redo this process, if not dozens or hundreds of the times. Clearly, if I'm I keep run long-time trajectory and binning it, it's going to be very expensive for each evaluation. That's why I also need a new model. I cannot just keep running the dynamical system and obtaining that. The very nice connection, again, by the definition of the physical measure or by the definition of the invariant measure. This is from a paper by Lagrangian in 2002. So this is the definition for invariant measure mu star. Okay, so f is a test function, and it can be any smooth test function here, which will see infinity. But now if I choose f to be related to my velocity v, and plug into the same equation that we have on the top, we have by the change of variable and also some integration, you actually get this integration in the end has to be 0. So again, phi here is a test function. And the fact that this equal to 0 for any test function phi telling me my invariant measure is exactly a stationary distributional solution to the continuity equation that we have seen many times in the past 2 days. So this gives me approximately a new model, right? Because if there's a connection, this is the same V, the right-hand side of the dynamical system. But now instead of running the time trajectory for 2 million time steps, I can just try to find the invariant or the stationary distribution or stationary solution to this continuity equation then I can get an approximation to my invariant measure. And in inverse problem, that's me evaluating the forward map. And I have a much faster way to evaluating it rather than each time I have a guess for theta, I run it like millions of time steps. So now it also gives us a very nice model. And so far we have changed the data from trajectory to invariant occupation measure. And we also have a model that is the continuous equation steady state solution rather than the ODE itself. So just to summarize the idea from Lagrangian to Eulerian, our starting point was to find the parameter in the dynamical system. And the intermediate step is to change your observed data into our occupation measure. And in order to model that, we realize there's a connection to the steady or stationary distributional solution of the continuity equation. And on the right-hand side, what you are seeing, it is the Lorentz system after running long enough. So they convert to this attractor, which is a two-dimensional manifold in this three-dimensional space. So now we have this model. So again, to see that our proposal was, instead of solving the inverse problem as an ODE-based problem, PDE-constrained optimization, we solve it as a PDE-constrained optimization, because now my forward problem give me a parameter, I solve the continuity equation, I get the solution, and then I compare with the truth reference data. And then the inverse problem is also based on the continuum. And once we are in the PDE-constrained optimization regime, there's actually a lot of literature, especially from Europe, that about how to do that, how to compute the gradient, how to analyze all the properties and optimization algorithms. And that's also what I did for my PhD. So that's a part of a familiar ground. Okay, so now after this all changes in the data and also the change from the model, now we are dealing literally a PDE-constrained optimization. And the problem is similar to something we saw yesterday. If you are dealing with neural network, you want to find this theta, and the theta, as I mentioned earlier, can be your neural network weights, or can be a coefficient for polynomials, or can be rho beta sigma, the physical parameter. Well, rho star is the occupation measure you observe from the time trajectories. So we need binning. The good news is you only need binning once. You only need to do this histogram for your observed reference data. Okay, while the model is the steady state solution to the continuity equation at this particular parameter theta. So this problem really become like a standard PDE-constrained optimization. While D is chosen as a property matrix that can capture the essential differences between my reference distribution or reference measure rho star versus my synthetic rho theta that come from this continuity equation. So for example, a very good choice of D will be the Wasserstein metric, and here we use the quadratic Wasserstein metric. So the reason and the goal here is the forward problem have changed, dynamical system to PDE. The data has changed, trajectory to occupation measure, but the parameter never get changed. It's still this velocity. So the parameter is still embedded in my in my PDE model. So that's the nice thing. That's the connection of these two different frameworks. And the motivation of doing this change is that now you are more stable. At least what I mentioned earlier, initial condition influence is gone. Noise is also more robust. And also not to mention, we are using the Wasserstein metric to compare. Okay. So in terms of how to solve the forward model, I'm just going to comment a little bit. So the forward model now becomes solving the stationary distribution to the continuity equation. And so here we use first order Adjoint scheme that you saw yesterday from Dion's Antonio's talk. Okay, and also as I mentioned yesterday that finite volume method, the way that you are solving it by finite volume method, you are already in a weak regime because finite volume is integration in each spatial cell. So it's already a weak solution to the original PDE. So that's fixed perfect that the original model is also a distributional solution. So we discretize it still as is time dependent, but once you discretize by Adjoint scheme, you actually obtain a very nice Markov matrix. that's the beauty of Abwin scheme. It allows you to have a conservation of mass and a positivity preserving. And in terms of linear algebra, it means you have a Markov matrix. Well, the problem becomes, how can I find a rho such that I'm rho equal to rho? So it also becomes eigenvalue, eigenvector problem. But the good news is you already know the eigenvalue. The eigenvalue has to be 1. So the rest is sparse linear algebra. So although it gives us a Markov matrix, so we regularize a little bit by this well-known page rank, Google's page rank trick, which is called the teleportation. So we regularize the original Markov matrix as a linear combination between this one epsilon of the original one versus epsilon of this new one. This new one is just one entry in 1 over n in every component. But by this regularization, M epsilon theta will have strictly positive entries, and based on the Poisson-Frobenius theorem, you guarantee to have a unique solution. So that's in terms of numerics, that give me unique eigenvector, and that's also give me a better condition number, which means I can find the solution in a much faster speed. And once we do the regularization, the solution can be found by sparse linear solver. And I want to comment in a 3-dimensional case, this step of finding the station distribution range from 8 seconds to 20 seconds based on your mesh. So this is nothing compared to running time trajectory for 2 million steps and do the binning. So it's a much, much faster way of obtaining a surrogate model. Okay. So next, I want to comment a little bit the choice of the Wasserstein distance to compare the reference occupation measure and my synthetic stationary distribution. And here we use the Wasserstein distance. And there's 2 reasons I want to use Wasserstein distance, and it's rooted to what I did in my PhD. So one thing which is also part of the program's name, the Wasserstein metric really captures the geometric information. And when we are dealing with such physical problems like wave equation based inverse problem or this based inverse problem, there is intrinsic geometric change embedded in your forward model. And if you use Wasserstein distance, you can capture, for example, things like translation and dilation, and it's convex in terms of those simple changes. And if my model dependence from theta to rho is also such changes, then this is a perfect choice. And this is something we have investigated a lot in wave equation-based inverse problem. So I don't have time to address that, but just to show you visually the fundamental difference. I have 2 waves, and I want to infer what's going on underneath the ground, right? I only can do this matching between the synthetic data and the reference data to find what's going on under the ground. And it's optimized PDE-Constrained optimization. And on the left-hand side, you saw by using least square, nonlinear least square method, least square L2 norm as objective function. And we cannot reconstruct. You can see the residual rarely decrease after a while. That's technically a local minimum. While the Wasserstein distance, they start with the same initial, we will be able to diminish a lot of the data residual and in the end reconstruct Mammoothy model. So this is because we were dealing the wave, and the change between the wave time domain data and the velocity is most likely translation and dilation. So that was a very perfect use of the Wasserstein metric in terms of its properties. And now there's a lot of people doing things like this, from Cost and France and China, etc. So one thing is the geometric feature that is really nice, like to capture my fundamental inverse problems, continued dependence between theta and the rho. Another thing which, before I go into another thing, I want to show you in this chaotic dynamical system reconstruction, you also have a translation and dilation. So the red one is the initial dynamics. The blue one is the reconstructive, while the green one is the ground truth. So you can see changing from the initial to the truth in 3-dimensional, you have to stretch, you have to do a translation. And that's another thing that I think Wasserstein distance will be perfectly for. And the second reason why we like Wasserstein distance in this situation is insensitive to noise. And there are 2 lines of work I have so far. One is from Felix and Villani in the Telegram paper. They found the connection between W2 and H-1 semi-norm. And the recent Remy Prairie has a paper also proving the equivalence between Wasserstein distance and H-1 semi-norm. So what is H minus 1 semi-norm? It is a weak norm and it is insensitive to noise. So that's why in this situation, when I have very noisy data as my reference, I will still be able to reconstruct the Mamouzi model because Wasserstein distance doesn't see this noise because again, it is a weak norm. And also based on the fact that we transport, because we transport and we don't have to transport much to cancel out the noise. That's why we don't see it. So these are two main reasons why we use Wasserstein distance. And so next is now we have the model, we have the data, we have objective function. In terms of doing PDE-Constrained optimization, we need to differentiate. We need to be able to get the gradient. So we want to comment a little bit on differentiability of the Wasserstein metric, and that's the main part of contribution from Lavon in this paper. So now when we talk about the differentiability, it's now differentiability with respect to rho, which is probably the case that there's a lot of classical results like when you can differentiate Wasserstein distance, we can find in all the books. But here, since I don't really care about the rho, what I fully care about, what I really want to find is theta. So I care about the differentiability of the Wasserstein distance with respect to theta, and there's actually some difference between these two. So I just repeat what's the formula, and we want to differentiate with respect to theta. And the question is, when f is differentiable, when can I carry out the derivatives? And that's, I think it's quite a relevant problem when no matter you are doing neural network training or anything, you are using Wasserstein distance as a data matching term, you probably will encounter such a problem or such a question. But this formula is continually showing up in all the papers that we can ever find. Right? This is the counterarray potential between rho and rho star, and then this is d theta rho. It looks like a perfect chain rule. Right? We see this a lot of the time, but we didn't find a lot of analysis. But I think when people carry out the chain rule, they already assume both exist, and we should be able to do it. Okay. So it depends on how you are going to carry out the chain rule. In the Wasserstein distance, you can carry out the chain rule in the flat metric space, and that's exactly this red term give you the counterarray potential, and then you have d theta d rho. So that could be one potential way how one reach this formula eventually. Or we can do the chain rule in the Wasserstein matrix in the tangent space, and in that case, there is also a chain rule. Like it's just the derivative in the Wasserstein tangent space before you drag it down to the flat space. Okay, so you then carry out, you get exactly the same formula. So if they all exist, it doesn't matter which chain you will carry out. However, this is based on the fact that they all exist. The question is, if neither the counterarray potential exists, nor this d theta, this term, which is the rho's as a curve of theta, whether the derivative exists, if now let's say neither of them exist, then neither of the chain rule will work, which means you cannot use this formula. Okay, so that's what we were puzzled a little bit and try to see what the connection, what the condition we can actually use this formula. And the result is actually a little more general than what we thought. So here is an example where neither of them exist. So first of all is the counterarray potential. If we forget about theta, just think this is a problem between rho and rho star. Then in Sant'Ambrogio, in his chapter 7, there's like a page that is about this discussion. And in order for, that means counterarray potential should be, it's never unique, but it should be unique up to constant on this entire domain. But in this case, it's not unique up to a global constant, because in the middle, you can be anything. So in this particular case, it's not the counterarray, or the d rho, dw to d rho doesn't exist. Okay. In the second case, which is d rho d theta. So in the Wasserstein case, if we can replace theta by t, for example, in order to make this thing differentiable, rho need to be absolutely continuous with respect to theta. But this example is not absolutely continuous with respect to theta. That's another reason why it doesn't exist if you replace theta by t, for example. Okay, so this too is a counterexample where you cannot, this very simple case is an example you cannot use it. Okay, so we actually So what's going on is I just want to say the answer first. So although if you want to carry out from the chain rule, it doesn't exist, but by our result, this case is actually differentiable with respect to theta. It's just that you cannot justify. It's just that you cannot justify by chain rule. It's still differentiable with respect to theta, except one theta equal to 0. So it's just you cannot justify by theta. So this is something I would say a little bit contribution from our work. So similar setups like about differentiability, you can find a lot in non-parametric setting, which means there's no theta. It's just between rho and rho star. But new effects appear in the parametric regime, especially if you don't want to call the chain rule. So this is our result. So if the mapping from theta to rho of theta is nice, which satisfies some assumption we have in the paper, and then in order for you to use it, as long as the countervariate potential is constant, rho almost everywhere, rather than almost everywhere, then you will be able, or it's okay to use this formula because it's still got to differentiable. So I want to comment that this is actually different from what Santamabrado had in the paper, in the book in section chapter 7.2. He particularly had a paragraph saying, if there's no theta, you have to have the countervariant potential to be constant all everywhere rather than rho everywhere. So without theta, this is not enough. But with theta in there and with this map is nice. Actually, this is actually good enough. And then the next question is, when can I justify, or when will I be sure that phi2 minus phi1 will be constant rho almost everywhere, which means they can be constant when they can be different when rho is not supported or when rho is 0. So we give a sufficient condition when you can guarantee that. And the sufficient condition is called linked. So the question is, how can you guarantee that? So the sufficient condition is some definition of linked. So I think this is really hard to describe. So it's better to have an example. So let's say your domain, your rho is not really connected. So you have parts that the definition or is absolutely 0. So the support is disconnected. But if the mapping or the image under the transfer plan are also disconnected, the closure of the mapping is disconnected, then this is what we call not linked. But if the closure of the corresponding mapping are connected in the closure sense, they don't have to be connected, but it's connected in the closure sense, then we call this is linked. So in our result, we show as long as your optimal plan is like this situation, as long as this map are linked, then it will have phi2 minus phi1 constant rho almost everywhere. So then this is the theorem. So if it's mutually linked, yeah, then phi2 minus phi1 is constant rho almost everywhere. And if you refer to previous corollary, that means it is got a differentiable, which means you are safe to use this formula in terms of differentiation with respect to theta. So in the end, it turns out to be a lot more general rather than just chain rule by itself. So that's also a good news. So finally, we give an example here. So this is a particular example we created. Rho depends on theta. So I want to comment that rho theta is not absolutely continuous. So that's actually one of the chain rule will fail. And then this is not Gaussian differentiable because of the support for rho is disconnected. Okay, so the other chain rule will also fail. However, this is Gaussian differentiable. So this is saying that you don't have to call it from chain rule. You can just directly doing it as a function of theta rather than have to go to a function of rho and then a function of theta afterwards. Okay. So now let's think if the case, the assumption satisfied, we should be safe to do a derivative. We have a gradient, and finally back to the inverse problem framework. We need to do it iteratively to get the parameter. And thanks to the so-called Adjoint-State method, which is a very powerful method in the community of PDE-Constrained optimization, no matter you were using it for optimal control or inverse problems. This is give you a way to deal with large-scale inverse problem because you only need this 4 steps. And you only need to solve 2 PDEs to some extent to get the gradient of hundreds, millions. So yeah, no matter how many parameters you have. So at each iteration, we first solve for the steady state. And this is based on the Markov matrix I mentioned earlier. So that's sparse linear algebra, 8 to 20 seconds based on your discretization. Second, I'm using Wasserstein distance. So I would like to get the counteractive potential, since that is an important component for me to compute the gradient. So once I get the counteractive potential, I plug into this adjoint equation, which is formally an adjoint of the linearization of the forward problem. And I get something called lambda. And adjoint equation normally is very non-physical. But the reason you have adjoint equation purely because you want to do gradient descent. Okay, and finally with rho L and lambda L, this is your gradient based on the formula that we just showed. So this is our gradient. And then, this entire part is our gradient. And then you can do gradient descent, or even more advanced version, nonlinear conjugate gradient, or LBFGS. And this is the 1 iteration, and we do it again and again until we find the parameters. Okay. Yeah, I want to comment, since this is like a few seconds, then this is also a few seconds. So Wasserstein distance in 3-dimensional right nowadays is not too bad. So this actually doesn't take a lot of the time if your discretization is not too fine. It's still trackable. So let's look at the numerical examples. First is the synthetic case in the sense that I get my rho star actually fakely from the continuity equation. So in inverse problem, we call this inverse crime because the data is from the same forward solver that you obtain the forward solution. So in this synthetic or inverse crime situation, there's no modeling error because you use the same model to generate the data. So we can find the sigma rho beta, just find that it's correctly very, very fast. And there is a multi-parameter phenomenon, and it's common in inverse problem. If you want to find the parameter, 3 different parameters simultaneously, they interact with each other because each time the gradient is by assuming the other one is correct. So when you do them simultaneously, they may not really go into the direction that help you to go down. So one way to deal with that is to do the so-called coordinate descent. So 1 iteration, you only do 1 of them. Try to avoid the potential interaction of each other. Okay. So this is the synthetic case. And the next case is a realistic case in the sense my rho star really come from the occupation measure. It comes from the dynamical system. And in this case, you can see we no longer can reduce the Wasserstein distance to absolute 0. And if I reduce my Wasserstein distance to absolute 0, I'm overfitting terribly. So that's why you can see the distance no longer, which is good. Maybe I did it on purpose. I don't want it to be absolute 0. And also you can see some overfitting phenomenon by looking at the model parameters error, especially for beta. It go down to 0 first. So it was as the truth. But because of the overfitting in terms of the modeling error, it go up again. And a similar thing you can see here is go down and then go up again. So that's because there's still some modeling error between my occupation measure accumulated from the dynamical system versus the continuity equation steady state solution. So that's something I definitely, well, most of the time I think it's a numerical error due to the first order finite volume method that a lot of people in the numerical analysis community will laugh at me. But although we didn't get absolutely perfect parameter, we can just try to see the reconstruct parameter. The reconstruct dynamics. The reconstructed dynamics match in shape or in the global feature like the original, the blue one and the green one are pretty good. So that's the parameters. So they were not absolutely the correct. So you can see correct is this 10, 28, 8/3, very classical set of parameters. But what we reconstruct is not absolutely like that value. So this is the 3-parameter case. So you may want to ask me why I spend so much effort like doing Wasserstein distance continuity equation, in the end just find the 3 single scalars. Of course, the ultimate goal is now just to find 3 single scalars. And that's what we actually did after this paper. And this is joint work with Jonah Botvinnik Greenhouse, who is a first-year grad student at Cornell. So we want to test whether the framework can actually work with variable coefficient. And the first scenario we work with is just to simply change the Lagrangian system. from a constant coefficient to a variable coefficient. Then now after discretization, sigma is no longer a scalar. Sigma is based on my mesh in 3-dimensional. That's easily almost like a million of them rather than 3. So now the stress is high. So I want to see if the framework can still reconstruct sigma, rho, and beta. But more importantly, not about sigma, rho, and beta, I really want to see if it can reconstruct the dynamics, because I'm clearly over-parameterizing my right-hand side. Lawrence tell me 3 parameters is enough, and now I'm making it this large. Okay, and again, I want to comment, due to the beauty of adjoint method, the complexity of computing the gradient is exactly the same as before. You didn't waste any more time. So solving this side of the problem versus the earlier problem is exactly the same computation, plus some discretization of the storage of the mesh. So this is actually the reconstructed sigma, rho, and the beta, since they are 3-dimensional object. So I'm just showing their 2-dimensional projection in this case. Each of them is a function of 3D. So the ground truth is, of course, absolutely a constant. But what's interesting is we didn't reconstruct a constant. And moreover, what we get reconstructed, what's really different from the original, is highly correlated with where your attractor was located. So that's something very interesting. And also in inverse problem, we have a saying, when there's no data, then there's no parameter. So if my data, which my invariant measure, didn't exist in that area, then my reconstruction in those areas may not be reliable unless you have some prior knowledge that, for example, you think is polynomial expansion, etc. Otherwise, you basically cannot trust them. Okay, so this is the parameter which is non-constant, but the dynamics look good. So although we are not using this, so this is the initial, the black one is the initial, where the initial parameter starting point. But the final reconstruction overlap with the true dynamics. And another thing we were doing very recently is the fact that to be a little bit more advanced, rather than just creating a fake Lorentz, is to try to reconstruct the chain system while the entire right-hand side is parameterized as a function of x, y, z. So we have 3 parts, so it's a vector field, so it becomes theta 1, theta 2, and theta 3. And again, after discretization on your mesh, there will be thousands of variables, but it doesn't really matter too much. It's the same complexity as you are solving this 3-parameter inverse problem due to adjoint method. So this is, it's on a very coarse mesh. The first column is the initial with the wrong parameter, while the middle is the final reconstruction, and the right-hand side is the target distribution, all in this 3D projection. So that's where I can observe my invariant measure, for example. And then this is the reconstruction change. This is the change between the initial to the final in terms of my parameters in the projection. So again, I want to emphasize just how much they coincide with each other in terms of where you see there will be a parameter update. And this is again due to the fact that if you don't have data in those areas, you really don't know the velocity in those areas unless you have actual prior knowledge about what's going on there. So because the way we parameterize it, or in terms of finite volume discretization, is basically piecewise constant for solder. So there's no actual assumption in what's going on globally. And that's why when we see the update, there's no update in this part at all because there's no data. And finally, we can see the dynamics like converging. So this is the initial, and the red one is the true dynamics. And then there's the final, like the blue and the red. So we are still working in terms of this direction. So finally, I think we are perfect on time. I would like to draw a summary. So the entire idea was built upon the fact that in this regime, or in dealing with dynamics, we have these two connections, the Eulerian and the Lagrangian. And the interchange between each other actually can help us a lot. So I have a separate work in both my equation. I was exactly doing the other way around. I was turning both my equation into particles. That is Eulerian to Lagrangian, but this work is Lagrangian to Eulerian. And the nice thing is, I use some of my old training in finite volume method and computation for dynamic discretization that give me a very efficient way to evaluate the forward problem. because it's become Markov matrix, M rho equal to rho, a sparse linear algebra. And also because we are using finite volume discretization, the M is 3 tri-diagonal matrices added together. So it's really, really sparse. So that also contributes to the fact that we can solve it fast. Optimal transport, and why I like it, because the fact that it can capture the underlying geometric change induced by this map. And the reason we use the adjoint-state method is, unlike generative models or many other models, a lot of models in ODE or PDE is implicit, because exactly ODE and PDE, most of the time you don't have explicit dependence on its initial condition or on its boundary condition. It's all given to you as an ODE, which is implicit formulation. But adjoint-state method help you to get the gradient for implicit constraint. And finally, multi-parameter is always a hard problem in inverse problem. And there's for future directions. If I'm a numerical analyst, I would like to improve my final volume solver. Right now it's fourth order, so try to be better. And also right now I'm using continuity equation to approximate the occupation measure or environment measure I accumulate. Is there a better way to do it, or more adding some component to make it more realistic? As you saw earlier, there was some modeling error, and I want to reduce that. And this is also related to the third part. I want to reduce the model error, and that's otherwise I have overfitting. And so far, the three dynamical system I show are having a single attractor. But if it has multiple attractors, it means the Markov matrix will have several. So the dominant dimension, eigen dimension is not going to be one. It's going to be several. So how to deal with those situations? And finally, what I mentioned basically is one inverse problem in ODE and one inverse in PDE. I see there's some connections, and it motivates me to do it from one way to the other. But it's important to know when I can do it and when I cannot. And those connections is also need further analysis. So thank you very much for your attention. And I would like to thank especially Adam Overman, who make this collaboration feasible, and also the fact that IPAM was the platform for us to meet together. Well, my collaborator I never see in CD. Thank you very much.
Yunan, thank you very much for sharing these nice ideas. Maybe you have time for a very small question. So 1, 2, I guess you were first, Nicholas. Let me bring you the microphone.
I hope not to disappoint with the question. So, here you're assuming that you observe the full state.
Yeah.
What happens if you just have an observation of that? And maybe how would that be connected to maybe these methods that people use, like to analyze dynamical systems, kind of like from this geometric perspective, like using these delay maps and tacens embedding and stuff like that? I mean,
yeah, that's true. If we don't have a lot of data to be able to be a good approximation to the invariant measure, that will contribute to my model discrepancy, which means my continuity equation model is not a perfect model for that data. So that is definitely is a one problem. And I think the nice thing is here we don't require equally spaced time trajectory. It can just be randomly sampled. As long as you sample long enough, then we can have an occupation measure. So that's one flexibility, because for example, in order to estimate the time derivative, you need to have high quality. But here, you can also have noise, because noise cancel each other out when you add them all together. So there's some flexibility, but it's in order to have an accurate approximation to the environment measure, it needs to be long enough to some extent.
All right, I try to keep it short. Thanks, Yunan, for this very interesting talk. I have a question. So in classical inverse problems, you're typically facing a compact linear forward operator, which has a smoothing effect, like a convolution operator, for instance. And then since the eigenvalues of this operator go to 0, you cannot invert it, and you have to regularize, especially when your data is not in the range of the operator, right? But it seems like in these problems that you're looking at, it's actually the other way around. You have these hyperbolic PDE problems, or these chaotic ODE systems, where actually the forward map is extremely chaotic, and so you would expect that the inverse map is already regularizing, or a smoothing map. And so you made this point that the Wasserstein distance is a good choice because it's somehow robust with respect to noise. But it could be that it's just a general property of the inverse problems that you're looking at, that they are robust with respect to noise, because the inverse map is a smoothing operator.
Yeah, that could be very likely. I think based on a lot of empirical observation, using this continuity modeling, you are regularizing the problem. The reconstruction, as you can see, is a lot of the time are pretty smooth. So that work, unless it has to be pretty smooth to work. So there is implicit regularization. While using Marshall distance, additionally, maybe more like the convexity part, since it's nonlinear inverse problem.
Okay, thank you so much.
So maybe Yangxin, I guess, had something to ask.
No. Oh, we have time.
Yes.
Okay.
I'm gonna be nice.
Okay, thanks. So I have a question about the boundary conditions. So here, just by you're trying to get the invariant distribution, so you just construct this m theta, and you assume automatically it's a Markov matrix, right? So do you just create the artificial box?
Yeah, I'll create a box and enforce zero
flux condition.
Yes.
So you just use a cubic box.
Yes, cuboid.
Yeah, I mean, if you just impose this zero flux condition, can you just make it, because I picture that your data is going to concentrate on, I mean, especially for this example, it's on two-dimensional law.
Yes.
Right?
Yeah.
Is there any way to just really create a box? It's not a regular box, but it's just a
not a regular box. Yes.
Yeah, just cover this range. Then you use a zero flux condition. This may reduce the computational complexity quite a bit.
Yeah, that's actually one potential direction, because right now I'm wasting a lot of box.
Yeah.
I'm wasting a lot of space. So that is one way. But then I think it's becoming the final volume discretization on a very irregular geometry.
Yeah.
But that will save a lot of computational complexity.
Okay.
Yes.
Okay, thanks.
Okay, let's thank again Yunan.
Thank you very much.
Thank you very much.